Hi, in this video, we want to take a look at exploratory factor analysis. All right, so factor analysis is the idea of finding or confirming, like under the hood, not directly observed, latent variables. All right, so what do I mean by that? Think about intelligence. Okay, so intelligence, if I want to measure that, how do I do that? I might give someone a quiz, might give someone a puzzle to work on, might give someone a puzzle to solve, some situation to work through, but I'm not actually measuring intelligence. I'm measuring their performance on a surrogate, okay? So if I'm looking at, if I'm looking at data that I believe connects to intelligence, I'm not actually measuring intelligence itself. I'm measuring some other variables. Okay, well, I believe that when I do this, I believe that there is some unobserved variable that's hidden, latent variable, that is driving the output, the results of these other measurements. Okay, so these other measurements are going to be called our indicators. There are our observed variables, and then the factors are what we're going to call the latent variables. Okay, so when I'm doing exploratory factor analysis, I'm taking data that I have and I'm checking to see, hey, does it look like there's any unobserved variables that are driving the observed data? Confirmation factor analysis is where we already believe that there are latent variables, and I want to run that model on my data, either to see, like, what do I have for my subjects in terms of the modeled variables, or I want to double check and say, hey, I'm running this again. Do I get similar results? Do I get similar, hidden variables? All right. So, in general, exploratory factors are uncorrelated, and confirmatory factors may or may not be correlated. All right. So, what will happen is that in a lot of the structures that we're working through when we build our exploratory factors in our modeling, when they're fitted, they'll be nearly uncorrelated most of the time. All right, well, when I establish my model, my factor analysis model, and I rerun it on some new data, now that data is what it is. That data is not the data that's being used for the fitting of the model. So it's going to be whatever I get is whatever I get. And so the correlation may be present, maybe not on upcoming data. All right, so factor analysis, we are assuming that there are underlying variables, latent variables, that are driving our observations. And what we're going to do, we're going to use correlation in some way, shape, or form to identify those variables and to model what those variables are after we have established models. So now, what version of correlation to use? That's up to us. We can actually use covariance, or we could use Terracore correlation. We could use Spearman correlation. Any correlation will work as long as it's appropriate for the data we have. Now, there's going to be something called loadings. Loadings are a measurement of how much a factor influences an observed variable. So loadings are super important in this topic. All right, so when I talk about the variance of my indicators, we're going to partition the variance into variance that's accounted for by common factors or commonalities, and another portion that is accounted for by unique factors. And these unique factors are largely not going to be observed by us. So the big hitters in factor analysis are going to be our loadings, our common factors, that is commonalities. If I look inside R, the stats package has a fact analysis function that will perform basic exploratory factor analysis, but this assumes that the data is multivariate normal, and it doesn't have a lot of options, so we're really not going to use that too much. The psych package has a whole lot more for us, a lot more utility, a lot more robust. Both of them are well established, but the psych package is where we want to be if we're doing factor analysis. It is so much more capable. All right, so let's go ahead and do an example. Now, this example is coming from Modern Psychometrics with R by Mayer, and I took the code from this GitHub website, and I just modified it to make it a little bit different, make it emphasize things I feel are more important. Change the code to how I like to write my code. All right, so for this first part, let's go ahead and let's take the R motivation data set, and let's go with terachoic correlation. All right, so remember the R motivation is this is providing like binary data. And if I look through the columns, there are a lot of categorical data that I'm really not interested in for this project. So what I'm doing, I'm grabbing only the external and internal motivation columns plus the hybrids. Now, when I do this, I'm also using smooth equals true to make sure I don't have any negative eigenvalues. If I look at the eigenvalues, we will have some that are within machine accuracy of 0. And so here, this just confirms that it was the right thing to do in terms of smoothing. All right, so now I want to double check and confirm that I don't have any negative eigenvalues. So I go ahead and take the minimum of all the eigenvalues, and I can see that it's basically 0. It's within machine accuracy of 0. All right, so now let's do factor analysis with 2 factors, no rotations, and we're going to use maximum likelihood. All right, so there are tons of options on how to do this. When it comes to factors, we can have as many factors as from 1 to the number of columns I have potentially. Now, we're almost never going to have as many as the data set I have, as many as my columns. I really want to have just a few. Now, the rotations we'll talk about later, but we're going to start off right now with no rotation at all. And then maximum likelihood, this is a good way for fitting. This is not the default way of fitting, but this works very well. Okay, so what we're going to do after I get the factor analysis, I'm going to go ahead and take a look at the loadings in particular, and I'm going to set a cutoff. If the value is less than 0.2, don't even show it to me. Just pretend it's not there. It's not part of it. All right, so what happens? If I look here, you see this list? I see that I've got hybrid, 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 and then intrinsic down here. Okay, so what this is indicating is that these variables, these observed variables, are kind of like grouping or connecting to one of the latent variables. All right, so what can I possibly call that? Well, that looks like an intrinsic motivation variable, right? It has all the intrinsics, and I'll bet you money that these hybrids are more intrinsic than external. Now, when I look down here, I can see that I see a group here, and I see that I have a bunch of external motivators. And then down here, I have some others that have smaller values that don't look as impressive. All right, so when I look here, should we conclude external? Yeah, you know what? I'll go ahead and put these into external. Maybe go up to here. I don't know. Now, like this one, probably go in the other one, but or we could just stop here. So let's go ahead and call that the ones that are the major players. So here it looks like these are the second column corresponds to external motivators. And then something about factor analysis is not all of our variables will connect with the factors we have. So I might not even consider including these in my factor analysis model. And here are some of Square's loadings. And we can see that about 10 of the variants, or so proportionately, 27% of the variance is accounted for by the first factor, and then just under 10% is accounted for in the second factor. Now, if I went through and I had as many factors as I could get, the proportions all together would add up to 1. And so if I was to go with cumulative and I had as many columns of data that I have as factors, the last one, the cumulative, would add up to 1. All right, so now let's take a look at the commonalities. And so here, bigger means that it's going to have more of an impact on our factor, or more of a connection with our factor analysis, our under the hood variables. And so we can look through and, we can see like these external ones are not coming into play very much. Neither are these hybrids. But when I get to, let's say about here, we have some, the values are getting bigger. And the interpretation is not always directly as clean as it can possibly be. Now, something that I do when I do factor analysis, when I'm trying to interpret what's going on, I take the loadings and I sort them for like just the first factor. And then I look at the biggest one in magnitude. Then I look at the variable that has the second biggest in magnitude. So it could be positive or negative. Then third biggest in magnitude, fourth, and all the way down the list. Then I move over to the second factor and third and keep on going. As I work through, as I go to smaller and smaller magnitudes, let's say on the first one, at a certain point I go, all right, that's small enough. I'm just not going to worry about it. I worry about the bigger ones. The bigger ones are the ones that are the most important. All right, these commonalities are a simple sum of the squared loadings and represent the proportion of variance. So squared multiple correlations explained by common factors. All right, we can see that the intrinsic items have high commonalities. Higher is better, whereas some of the extrinsic ones have low values. Okay, so now let's go ahead and plot this. Let's go ahead and do a plot where I plot the first factor and the second factor. And these dots represent like a grouping that we have that basically what it does, it takes the largest value. So here, so it's suppressed because of the 0.2 criteria, but this is bigger than that one. This one is bigger than that in magnitude. So hybrid 10 will be labeled with the first factor group. But look down here, external 1 has bigger for the second, so it will be labeled with the second factor group. Here, external 7 will be labeled with the second factor group, first factor group, and then second factor group. Remember, it goes by magnitude. And so when I look here, we can see the colors correspond to how it's being applied out. Now, I can also label it. So it's hard to see what exactly the variables are because I don't have their names. I have to go column number by column number, which is not really that convenient. I could go ahead and use the text function to plot it. And here we can see that we have, intrinsic floating around. Here we have external, and hybrids are kind of like in the middle somewhere, which is not surprising. All right, so when I am interpreting exploratory factor analysis, look at the loadings, look at the largest magnitude loadings first, and work down in magnitude. At a certain point, you say, all right, it's just so small, it's no longer useful, I'm going to ignore it. All right, so now let's do the same thing, but this time I'm going to add a rotation and a normalization. All right, this is not going to improve the fit of the model. The fit of the model is going to stay the same. What is going to change is that the loadings will change and the correlation between the factors will change. They'll no longer be uncorrelated. But the reason why I do this is my goal is to set it up so that I can interpret what's going on easier. All right, we have two types of rotations: orthogonal rotations and oblique rotation. So orthogonal refers to a matrix that's multiplying it, a matrix in the model building. And oblique means it's a non-orthogonal matrix that's doing the multiplication. All right, so oblique min is the default option. And you'll notice that that is a non-orthogonal method. Varimax is a popular choice that maximizes sum of variance of the squared factor loadings on the separate factors. Quantimax assumes that there's a single dominant general factor. So if you believe that there's like one big player that's really driving almost everything, my work with this in crime and in academic proficiency, this is the case for what I believe to be correct, that there is really like one major one, and then the other factors are much smaller in importance. Then Quantimax is a good choice for your modeling. Equalmax tries to do a compromise between the two. All right, so orthogonal rotations add an extra step of multiplying the loading matrix on the right by an orthogonal matrix. If you don't know what that means, don't worry about it. The textbook goes into deeper details about this. And so here, once again, I'm getting two factors. I'm using Varimax for my rotation using maximum likelihood estimation. And let's look at the output. All right, well, here I can see these values going to be, I think these are looking bigger. A little bit easier to interpret when it's more clear that it belongs in the factor. Here, it looks like these external ones are going into the second factor. And down here, we have some smaller values, which I may or may not consider including in my latent variable. And so here, the proportional variance is 0.25 and 0.11. All right, so how does that compare to what we had previously? All right, so it's a little bit, so 0.25 is a little bit less, but 0.11 is a little bit more. And we get about the same cumulative between the two. All right. Now here we have our commonalities. Remember that big is good. So I'm looking at the big ones first. And then here, these are the ones that are probably not going to be very influential or connected to any of the factors that were detected by my data. And we can plot this. And if you look at this and you compare the two, they look very similar to each other. The rotations do change things, but they're still in like the same neighborhood of the plots. Now what I'm going to do, I'm going to plot both of them together where I've got, I jumped ahead. Here is the text version of this, just so that it's easier to see which variable corresponds to what. Now I'm going to put the two factor analyses together to see how things move about by doing the rotations. All right, so the unrotated version is the steel blue, and the black is the rotated version. So we can see that the external 8 moved a little bit to the right, external 12 moved to the right. Sorry, it moved to the left when we rotated, moved to the left when we rotated. Hybrid 7 moved down, or moved up. But, we can look through and just spot the difference. All right, so now we can have as many factors as we have data. Usually we have a relatively a small number of factors, but potentially I could make it big. So let's just go ahead and go one step further. Let's have 3 factors. And I'm going to use oblique rotations. And I'm going to go ahead and use maximum likelihood once again. All right, so orthogonal factors have 0 correlation. Oblique factors are not independent. Okay, so remember that oblique factors are not independent. So something about this, if I'm modeling something and I believe that things should not be independent, then orthogonal really doesn't make sense, because it makes the assumption, or the output will automatically have 0 correlation. That doesn't mean it's independent. It means that we have 0 correlation. Now that's enough if I'm in a multivariate normal situation. 0 correlation and independence are the same thing. But if I'm in a more general situation, there's a difference. All right, so most situations, we are assuming that the factors are not independent. And so oblique models are attractive for this, because we're not getting a result that we know has to be inconsistent with the model. All right, so oblique min and promax are popular oblique rotations. All right, so let's go ahead and run through this. And so you'll notice that if I take the correlation off of these guys, if I get the correlation of my factors, this is not zero correlation. We can see that there's actually a 0.51 correlation between first factor and third factor. Oh, okay. I mean, that's enough that we can't just, if I wanted independence, I definitely can't ignore that. 0.12, I might be able to fudge it and say, yeah, that's close enough to zero, but 0.5, nope. All right, so now let's take a look at what do we get. And now we can see that the things look a little bit cleaner in terms of the numbers. We see that less overlap. So, all right, intrinsics and these hybrids are in the first factor. These external are in the second factor. And we can see here that these hybrids are in a factor. And these ones down here, we're probably going to exclude from our from being connected to our factors. Now here we can take a look at our communality. And now let's plot. Okay, so we see that we have a pairs plot on our factors. All right, we're used to that. We're okay with pairs plots. But how did these dots get colored? Like, what do the colors mean? Ah, I'm glad you asked. If I look up here, what's a good one? All right, let's look at hybrid 2. If I look at hybrid 2, its largest loading corresponds to 3. So its hybrid 2 is going to be colored by the color dot that corresponds to 3. Okay, so let's look down here. When I look here, I can see that the blue has larger on factor 2. I see that the black is larger on factor 1 because it's higher up, and then the red is small on factor 1 and factor 2. Okay, here I see the black is larger on factor 1 but smaller on factor 3. You notice that it's to the left. Down here I can see that the blue is smaller on factor 3 and smaller on factor 1, and the red is big on factor 3, small on factor 1. Okay, so I know that the black corresponds to factor 1. I know that the red corresponds to factor 3. Now, moving right along, when I look here, we can see that the blue is larger for factor 2. It was also larger here. So I know that the blue corresponds to the ones that are in factor 2. And then we have smaller values for the black and the red for factor 2. Not surprising. And so let's go ahead and plot it just to see what it looks like so I can get an idea of what's going on. And if I was doing a factor analysis, I would go through one by one, finding where each of them are before I would actually launch this model. All right, factor scores are the estimated values of the latent variables, the under the hood unobserved variables driving our observed data. So this corresponds to like dimension reduction in principal component analysis. And we can actually use factor analysis with these different rotations to perform dimension reduction if we wanted to. But usually in terms of psychometrics, that's not done. All right, so for factor analysis, let's do another example. I'm going to use two factors again. I'm going to use an oblique rotation. We're going to use maximum likelihood, but we're going to make it a little bit interesting. We're going to go ahead and do imputation with median, and I'm going to change the correlation type. But wait, there's more. If you look through the previous code, I passed a correlation matrix into the FA function. What I'm going to do now is I'm going to pass the raw data itself. The raw data is going to get imputed, and then it's going to measure the correlations. Then it's going to use those correlations to figure out our factors. And so we have two factors. We're doing Varimax, maximum likelihood. We are going, so by putting missing equals true and impute equals median, it's automatically going to impute. Now, my options for imputation, if I'm going to let the psych package take care of it for me, I have median or I have mean. Those are my only two options. If you don't like univariate imputation, impute the data manually yourself before you do this. And there are three different versions of the Yule correlations to go with. I chose this one because it made the most sense because it goes off of 2x2 contingency tables using the determinant and the numerator. And now here I can look at the loadings. And things are looking pretty consistent at this point. And then we have our communalities coming out. And I can plot it once again. And if I go through and actually inspect each of the scatter plots, I can see that these are actually pretty consistent with each other when I only have two factors. But there will be some differences. All right, so now let's go ahead and compare the output that we got. The only difference between these two was that with the black, I use tetrachoric correlation. With the purple, I use Yule-Bonic correlation, and I did imputation. The rest was the same. And so we can see the difference. So like globally, things kind of like got squeezed in towards zero, towards the origin. But things are not too far off from where they were before. All right, so something about this. We've been talking about factors, and we've been just kind of picking a 2 or a 3 as we went. How do I decide on the number of factors? How many factors should we use? We have tons of tools to figure this out. In fact, it's to the point where we have too many, so we have to interpret multiple things. So let's go ahead and do an example. This time I'm going to use the youth depression data set from the textbook package. And I'm going to do polychoric correlation. The first criteria is with eigenvalues. What I want to do, I'm going to take the eigenvalues of the correlation matrix. The eigenvalues of the correlation matrix correspond to the amount of variance accounted for by the factors. And so I'm going to plot the eigenvalues, and it's going to form a scree plot. I'm going to go from biggest to smallest, and it's going to create a curve. I'm going to look for when do I see diminishing returns as I move from left to right. And so here you can kind of see that. So when you look at this, if you say elbow, you'll come upon multiple elbows. Like, frankly, you'll probably call all these an elbow right there, because here you see a pretty big flattening. I think it's even more flat. And then these guys are all just kind of like on one slope. So I definitely would not go out this far. 5 would be the most I would consider by the elbow method. And then greater than 1 is also another criteria. And so here, this comes from a little bit more of a linear algebra point of view on eigenvalues and magnitude and mapping. So some people will say greater than 1. Some people will say find the elbows. Both have their advantages and disadvantages. And here we can see how much does each eigenvalue account for the variance and what's going on. So here we get 41% of the variance off of just the first one alone. Then we pick up another 7% if I go with 2, another 5% if I go with 3, and so on. So a relatively small number is appropriate. Now, another thing we can do, I can go through and I can randomly generate data by just basically permuting the columns of the data set, rerun these eigenvalues, and do this over and over and over until I get an idea of what's going on. And what I'll do, I'll compare my data to the situation where I have this random generation of data that univariately match my real data in the target variable, but in terms of correlation, correlation is shot in the random uncorrelated data. And so here, the red is going to be the simulated and sampled data, and the blue is the actual bit. So while I'm looking at 2 or 3, I definitely wouldn't go above 3 for this one. Now, very simple structure. What this does is that this sets a bunch of the loadings equal to 0 and looks to see how do the resulting factors perform with our data. All right, so here, this is the number of factors we have, and this is using just one loading in each of the factors. All right, so here, all but the largest loading value, and that's largest in magnitude, is set equal to 0. Here, I take the loadings, and all but the largest 2 are set equal to 0. Here, all but the largest 3 loadings are set to 0, and so on. And so here we see that like it flattens out, which kind of shows that there's not much improvement by having more factors. So I am thinking, probably 2 off of this one. And here's the output from the very simple structure. And there, there's BIC here. There's other things to help us, help guide us on what's going on. Root mean squared error approximation is an important one. We have Bayesian information criteria, complexity, a chi-squared value. So this is the chi-squared statistic, not the p-value, by the way. Now we can also go with hypothesis testing, root mean squared residuals, and Tucker-Lewis index. So here, if I run summary on my factor analysis object, one thing it's going to do is it's going to run a hypothesis test for me. And the null hypothesis is that what I have is sufficient. I'm not missing anything. If I reject the null hypothesis in favor of the alternative, that's saying I missed something. So the null is I have captured all of the necessary factors. I may have excess. The alternative is I am missing one or more factors. And we can see that if I run this with just one factor, I get a p-value that is practically 0. So I conclude that I missed one or more factors. Now we can also use the root mean squared of the residuals. And so here, if I use this criteria, a good fit is less than 0.05. A fair fit is between 0.06 and 0.08. A poor fit is greater than 0.1. So here we can see that we've got what? Fair fit? Yeah, it's on the boundary. And the corrected root mean squares of residuals is still in the fair region. Now, Tucker-Lewis index, what this does, this compares like the ideal best model possible and the extreme worst model possible with our model. And it takes a ratio. It takes the worst model statistic minus our model, and then divides by worst minus best case scenario. And that ratio gives us our Tucker-Lewis index. And so we get some values here. Now for Tucker-Lewis, we want better than 0.9 for a good fit. All right, another thing that we can do is we can try different number of factors and compare the results. And we do this with the Infactor function in the site package. Now, there's an entire package for Infactors, and so that has plenty of tools. I'm not going to get into it here, but plenty of options. And so here, it does it very nicely that I have my very simple structure, tells me my complexity, my empirical Bayesian information criterion, my root mean residuals, and then it gives me all this output to help guide me. Very nice. Now, what is actually the most important aspect to factor analysis? the most important aspect is the goal of the project. All right, so if I come up with factors that my audience can't interpret, my audience doesn't trust, or I can't interpret, then my factor analysis is crap. So I need to make sure that I am producing a model that supports what my actual goals are. So this might mean that you might go with a number of factors that you don't actually like, that statistically are not the best, but they're going to be accepted by your audience. And that's more important than anything else, because remember, a model that is not accepted by other people and not used is useless. A weaker model that is used is superior to the best model ever that gets thrown in the bin. Now, we can use subject matter knowledge and experience in the field to guide us on how many factors to use. So if I'm working on something, let's say that, and this is one that I've actually encountered with work. So let's talk about education data. My personal factor analysis that I've worked on shows that the #1 factor is kind of like an overall academic ability. Well, if you think about overall academic ability, that means that there's like science, biology, math, writing are all driven. Social studies also. So all the topics get driven by this. And so this first factor is just saying that, generally speaking, if you're good at math, you're good at writing. If you're good at social studies, you're good at science. Okay, now, what's interesting is the second factor will be something like, oh, I'm more of an English person instead of a math person. I'm more of a math person than an English person. The second factor, from my experience, supports that. But here's the rub, is that it accounts for much less variance than the first one. So overall, because of the magnitude of the variance from the first factor that I told you about, is that if you suck at one, you suck at the others. I mean, that's really what it is. So if you're lousy at one topic in academic, you're probably lousy at the others. That's just from my work with education data. You can prove me wrong by getting some education data and running it, but that's my interpretation from the results I've seen thus far. And I haven't seen anything to contradict that yet. All right, well, that's all I've got for you. Take care and goodbye.